All right, so we'll pick up where we left off last time. You need to know the particle box. The particle box will be tested heavily. I expect you to know the eigenvalues, I expect you to know the eigenfunctions. I expect you to be able to take and apply it to whatever type of problem that you're given. So make sure that you really know it. The reason it's so tested so heavily is that pretty much everything else mathematically is pretty tough. So it's the one thing that I can ask a lot of questions about. Everything else is going to require some really, really tough math. So because quantum gets so tough so quick, you don't tend to ask a lot of other stuff. Remind you what we finished up with. And then I want to take a look at kind of some of the finer points. We talked about this a little bit at the end of the class last time. So we had HC over 8 times the rest energy times L squared. We talked a little bit about the fact that that's 1240 eV nanometers, or if you're working in something that's got a link here of fermis, then that's going to be 1240 MeV fermis. Those are the two most common ones, because usually you're talking about something that's the atom, and the atom's on the order of angstroms, which is 1/10 of nanometers. Or you're talking about the nucleus, and you're using this as some sort of way to approximate nuclear levels. If you're doing nuclear engineering calculations, for instance, for Comanche Peak or what have you. And then you're talking about those things being fermis, so you're working with MeV energies. So that's the two most common. But it could work for anything. And in fact, you could make a box that's bigger than an atom. And the way you would do that is that you confine, for instance, the electron with a group of atoms. Now, how could you do that? Well, you build a crucible or something. And so the electron could be thought, who knows what it really looks like, but you could have some sort of mental picture of it being something like this. You got like this group of atoms kind of like this put together. And this electron is kind of like able to just kind of swing around here anywhere he wants between all these atoms. He's not actually owned by any one atom, he's kind of free like a gas. And maybe that's in some sort of structure like gallium arsenide, but then on this computer chip over here, if you were to look at it, there'd be like this piece of gallium arsenide, whatever, would be like that. And then you've cut and made some sort of break, and then it's some other material. So it's confined in this area. There's all sorts of structures like that. They're called quantum dots, for instance, if you make them a thing. So they can be quantum wells. And people can build any type of structure, and they can make those structures confine this electron. And what they do with that is that changes the energy levels, and that enables them to make different types of light. So you can make a blue LED laser if you're wanting, or a UV laser. So you can make this to write, for instance, to a hard drive, if you want to read a hard drive. But you can do lots of other things with it. There's almost no limit to what you could try to make it so that the use of wave function is a way of doing really fast computing. Because as soon as you ask the information for the wave function and he gives it back, it's instantaneous. If you make the wave function very complicated, you can put, for instance, 4 billion mathematical steps into the wave function. And so immediately when you ask it, it does 4 billion mathematical steps simultaneously. And they could be as complicated as a calculus step, or they could be a Laplace transform, or anything. This leads to the idea of quantum encryption and quantum decoding and quantum computers and so forth. But you got to figure out how to make this thing. Then you got to figure out how to build that wave function. So that's non-trivial. And then you got to figure out how to fabricate this onto some sort of a chip. And that's a non-trivial stuff. But that's where the world is going. Because in the quantum world, I'm not limited by the speed of light. Because it doesn't actually go through space. It's everywhere and nowhere at the same time as a wave. And when I observe it, I can instantly get the information out. So I have no limitations of relativity like I would if I'm sending a current down a wire. So I can think of computational speeds being 15 orders of magnitude faster than today and make your calculators look like you're counting on your fingers. Problems that you can't work in the past are suddenly completely possible to be worked in the future. This is where we're going, and another reason why, if you want to be in the modern world, you're going to have to know modern physics, which is a misnomer. because we're talking about 1920s here. All right, so that's not so modern if you really want to get down to it. Modern, it's not in the classes. It's in the research journals. It only gets in the classes when things are 30 years old. So if you want to build state-of-the-art devices, you've got to learn to be able to read the literature. And the literature doesn't have examples and such. The literature is written by people in 4 pages. They've just given you 2 years worth of work. So you've got to be able to read. So by the time you leave, we have to get your ability to read books beyond textbooks and into reading journals. Another reason why undergraduate research is so important. So you can confine, if this thing, each one of these was an angstrom, you could confine this to be what the length of this box is, and that box might be a micron. And so if that's a micron, then this L is changed. And in that case, then this thing, you'd want to use what's useful for that, and that'd be milli-electron volts per micron. So I can adjust that length to make it anything I want, and I can adjust this to change these energy wells any way I want. So we really like this. Now there are other shapes and more complicated, but this is the easiest thing to build. This is the easiest thing to solve mathematically, and that's why we do it. So if you don't know this, you just want to solve the Schrödinger equation for really hard stuff, I guess. This is the easiest thing we can have. It says find the first 4 energy states of electron confined to a well that's 2 nanometers. Let's go ahead and do it. I think I actually did this, but I didn't punch in the numbers. So this is EV nanometer. Oh, that should have been squared. And then this is over 8. Now, this depends on the particle you have because the MC squared, and how I got the C was I put a C squared on top, I had to put a C squared on the bottom. This was just P squared over 2M. The M was already there. So what's the rest energy of an electron? There you go. So again, things you want to know. 1 times 10 to the 6th EV. It's advantageous if you can work in factors of 10 to the 3rd because this one has a 10 to the 3rd. So this is 1.24 10 to the 3rd, and then you're going to square it. So you're going to get 1.2 squared. Now that's like 12 squared is 144, so 1.2 squared is 1.44. So I can do that roughly in my head. So that's about 1.5. And 10 to the 6, but the 10 to the 6 will cancel the 10 to the 6 here. So I got about 1.5. I have about an 8. I have about a half. So a half times 8 is 4. So I got about a 1.5 divided by 4. And then I've also got over here 2 nanometers squared. And so I'm going to be left with one of these EVs is going to cancel one of those. So I'm going to be left with a single EV. So it's going to be electron volts. Like I said, I got 1.5. I got 4 times a half, that's 2. So I got 16. So I got about 1.5 divided by 16. If it was 1.6 divided by 16, it'd be a 10. So it's a little bit less than that. Take your calculator and punch it. But it's not even going to be an electron volt. It's going to be like a 1/10 of an electron volt. All right, what did I do wrong? 1240 squared, good, no problem. Divided by 8, yeah, divided by 2, divided by 0.1. Oh, I didn't divide by the square of the 2. Again, why we check our numbers so we make sure we do things right. So En is 0.094. So like I said, a little bit less than a 1/10 of an EV. And then that's times n squared. So there's 1, there's 2, 3. And remember, the spacing gets further apart as you go up. So this is 0.094 electron volts, or if you prefer, 94 milli electron volts. This one is 0.368 electron volts. This is 0.828 electron volts. And this is 1.472 electron volts. So there's the first four energy studies. And exactly like we did before, now that you got the energy diagram, you can go and be asked questions like, what's the photon that would be emitted as it went from here to here? Or how much photon energy is taken to go from here to here? So the idea of building the quantum well or such is that before you had the atom, and then the more atom, you had no choice about its energy values or whatever they are. But with this thing, I can change the L, and I can adjust these levels to anything I want. It's like being able to make your own atoms. So you can build any type of structure you want, and therefore you can get any type of light or absorption. So build any type of detector, I can build any type of emitter that I want. And that's what electrical engineers do. They adjust things around to make whatever they want. Now, problem E says, or F, find the wavelength of the photon emitted when the electron moves from the second excited state to the ground state. All right, let's see who doesn't mess it up like on the test. Second excited state is n equal what?
3.
3, not 2.
That means I got it right on the test.
I'm there. Where's the ground state?
1.
So subtract the two energy levels and then use that energy, 1240 eV nanometers divided by that, and you found the wavelength. Just like you did on the test. The only thing that keeps changing on the problems for the rest of the semester is how we go about getting these guys. We're still going to always have a question on the problem, and then what type of wavelength do you get out? So delta E is going to be equal to E1 minus E3. Now that's the change in the energy, and that's minus the E of the photon. The atom's going to lose energy, so you're going to get a transition that's negative, but then that energy is going to go out to the photon. You know, a lot of you like to leave the minus sign off, that's fine, but at least make sure you know what you're doing. So this one's 0.094 eV minus 0.828 eV minus E photon. We'll punch your calculator again. And it's 0.734. That's minus E photon. So the energy went down by 734 millielectron volts, and it did that by giving off the 734 millielectron volt photon. So lambda is equal to HC over E photon. So 1240 eV nanometers, and you're dividing by 0.734 eV. Now, one of the things you'll notice is that you're going to be more than a micron long. So this is not a visible thing. This is in the infrared. And in fact, well, I was yesterday, Ben's thesis, which was really very impressive. He was applying infrared to kill cancer cells. And it's a way of doing double harmonic resonancy in order to image cancer cells and other cells inside the human body with his laser. So if you take 1240 and you divide by 0.734, you get 1.689 microns. So about 1.7 microns. this has that interesting importance to electrical engineers. For instance, if you look at silicon, around 1.2 microns, it is opaque, which means that you can't send it through. So if you're going to make a waveguide and you're going to send this signal down on the chip somewhere to some other part, you can't use regular silicon. You're going to have to use some other material. On the other hand, if you use another material that's actually transparent to this, doesn't absorb it, doesn't scatter it, then that's fine. And the silicon, if you put that in a trench, the silicon will act as like a barrier, and it will keep it in like you use a prism to do total internal reflection. And in fact, this is the idea in building optical waveguides on chips. So you will have your chance to demonstrate your knowledge of that stuff. That'll lead people in your later classwork. All right. Know the particle box build, do a particle box calculation. Other things I want to look at the particle box. Those wave things, wave functions. Go back and look at a little bit of what we came up with. So remember, this was 0 and this was L, and I'm not too good at drawing sine functions, so I apologize for my inability to draw. There's psi of x, and there's x. Maybe I guess we call that phi of x, because we left out the time. And this thing had a square root of 2 over f. How many humps does it have?
1.
1. What's the value? What's the n for the ground state?
0.
Wrong.
1.
1. You had a 50% chance of getting it right, and you got it wrong. A student in graduate school, he always had the right idea and the right explanation, and a 50% chance to get it, and whatever he would say by the end of the time, the class would just always choose the opposite. His logic was always right, but they choose the wrong thing at the end. Very bright guy. The number of humps is exactly equal to the quantum number n, known as the principal quantum number. The principal quantum number n is the thing that will determine primarily the energy for systems, including the hydrogen atom. So this n, this thing that distinguishes which one, is the most important, so it's called the principal quantum number. It has integer values. It has integer values for the hydrogen atom, it has integer values for rigid radiator, has integer values when you're dealing with the harmonic oscillator, and it has integer values in dealing with the particle box. You quantized it. You did by applying boundary conditions. It's universal to all of them. So the n tells you the wave function. It also tells you the energy value. For this particle box, it tells you the number of humps as well. So somebody says, draw me the first excited state or the second state. I don't have to know a lot. I don't have to sit and do a lot of math to do something like this. There's L, there's 0, there's L over 2. I need 2 humps. It used to look like that. That's n equal 2. If I give you want the 10th state, it will have 10 humps. And they will be spaced in a distance. Here you went from, this was L over 2, that was the first one. The next one is L over 4, that's L over 2 divided by 2. This was L over 2 divided by 1. If you have the 10th state, it will be L over 2 divided by 10. So there'll be an L over 20 and so forth. I don't need to do any advanced math to get exactly what the drawing is. These will be the most probable locations for the electron to be, because they're the humps. When I square this negative, it's going to be a positive hump too. Where's the least probable place to find the electron? L over 2 in this case. There's no probability of finding it there. You square 0, you get 0. Where's the average location of finding the electron? L over 2. How often do you find it? Never.
So
there's a difference between those two statements. An average is not the same thing as the grade. There may be nobody in this class that makes a 50, but the class average can be a 50. Half the people can make 100, half the people can make a 0. Class average is 50. Classically, what we measure is the average. That's what classical physics gives us. It's a large number of atoms, and we see the average. But when you're building a device with single atoms today, all that classical physics and that classical electrical engineering isn't true. It doesn't work like that. It works like the individual class scores. So V equal IR, that's a classical average. That doesn't hold. The device does not operate like that. What you get is individual values. Individual values for the energy based on the state, not the average. You could have 20% of the atoms in this state, 80% of the atoms over there. Actually, you don't even know the states till you measure them. All you know is that when you do a bunch of measurements, 8 out of 10 times it gives you this energy, and 2 out of 10 times it gives you that one. If you macroscopically do, you'll get the class average, but you will never measure that value in an experiment. You have to understand probability to understand how to build modern devices. You can't deal with probability, you can't deal with building devices. Plain and simple. You can't just, oh, it's kind of rough. It doesn't work. Something else you get out of this diagram. How many times between here and here does this cross the x-axis? None. Also known as 1 less than 1. That's the number of minimums. How many times does this cross? 1. Also known as 2 minus 1. So there are the n state has n maximums. That's maximum probability, n peaks. N minus 1 minimums. So if you're in the 10th state, there are 10 places where there will be a maximum probability of finding the electron, and there will be 9 places where there is no probability of finding the electron for the particle in the box. These are things you should know, be able to find quickly. Like last time, sometimes when you square it by symmetry or by looking at geometry, you can answer a question without doing the calculus. There's no doubt that the answer to where's the average location is to integrate over all space times x times psi star psi. Conjugate if it's a complex number. If it's not a complex number, then it's itself. Take the wave function, multiply by the wave function, then multiply by x, and then integrate it. So for the particle in a box, let's say we were at the n equal 1 state. This would be 2 over L, integrated from 0 to L, x sine squared of n pi x over L dx. So all that stuff we did back in chapter on probability is still all true. The only thing that's changed is I'm not giving you, for instance, a Maxwell-Boltzmann distribution. You have to get the wave function, square the wave function, to get the probability.
Dr. Marble, what is in the, after the x sine squared, what's in the parentheses?
N pi x over L. That's what the wave function was.
Okay. Awesome, thank you.
So in this chapter, he doesn't spend time going back and reteaching probability because he's already done probability. So instead of maybe this being constant or being a Gaussian or being whatever, you got to solve the Schrödinger equation to find the wave function. Then you got to square the wave function. Then you got to multiply by x. And then you got to integrate that. And that gives you the average location of the electron. Now, at least these are sine functions. Just wait till they start being those hydrogen atoms on that equation sheet. that you've got to start integrating. And they're three-dimensional integrals over theta, phi, and r. All right, so at least these are one-dimensional and the integrals aren't so bad. The integrals are going to get worse, and they get worse very quickly in order to find the probability. All right, enough on a particle in a box. Be able to work a particle in a box problem. Fortunately, the particle in a box was trivial. No, it wasn't trivial, but compared to what's coming, it was trivial. So the next thing he does is he says, okay, you know those infinite walls, they really weren't true. Oh, actually I got one more thing to do for this. Those infinite walls really weren't true. We're going to make those walls finite. Oh, that's going to make them math. Before we get to that, I need to finish one other thing I forgot, and that's superposition. So make sure you know that, like I said, and be able to solve problems both analytically and graphically. It will be a big part of the next exam. Yeah. It will be a big part of the next exam. I'm serious about that. You don't be able to do the math and you can't work the part of the box, you're going to take some serious major chucking chest wounds. Okay? Superposition. We found those states, the first, the second, the third, the fourth. Those are like energy levels. Okay? They're connected to energy levels. It turns out that there's no reason that the wave has to be a nice, you are in the second state sign. It can be any sum of those states, and it still would be an acceptable solution to the differential equation. So, if these guys, these sine functions, are states, think of them as vectors. Kind of like this. Remember classical physics, x, y, and z? And you can think about that we could just go along the x-axis, but we also could go like this. And be located out here. And it would have a certain amount along x, and a certain amount along y, and a certain amount along z. And the way you make this is you add, you know, maybe 0.2 I hat, 0.4 j hat, and 0.5 k hat. In other words, you add solutions to x to solutions to y to solutions to z. And these guys were called unit vectors. In quantum, these guys that we had up here, these eigenfunctions, they're the unit vectors. So the most general solution is so much in the first state, plus so much is in the second state, plus so much is in the third state, plus so much is in the fourth state. The only difference is how many states do we have? Like this. How many states are there? What's the largest value n can be?
Infinite.
Infinite. So you have an infinite sum. Oh, isn't that fun? No more three-dimensional spaces. Infinite dimensional mathematics spaces are now upon us. So, these sums can go to infinity. And each one of them is a constant representing how much and a state. And the states are these states. Now there's one other condition. The length of our vector has to end up at 1. That doesn't mean the phis add to 1, because what's the 1 is the probability. And the probability is related to the square of this. So if you think of each of the components representing how much is along that particular thing, the square of the length represents the probability you're in that particular state. So the square along x, the x component, would be the probability being in x. The square of the y component, the probability being in y. So the sum of these constants that go in front, when you square them, have to sum up to 1, 100%. So let me show you an example of that. You could have a wave function that looks like this. 0.6 times the second state, that's n equal 2, plus 0.8 times n equal 3. the probability that n is 2 is 0.6 squared. What's 0.6 squared?
0.36.
0.36. So 36% of the time, if you made a measurement, and you're going to make billions of measurements, 36% of the time, you will find that it's in the second state, and you will get E2 for the energy value. But you won't always get E2 when you make a measurement. If you look at the probability for n equal 3, it's 0.8 squared. And what's that?
0.6 squared.
Very good. 64% of the time, you're going to get the energy 9E1. So when you make a measurement of this system, you're not guaranteed to always get the same energy, even if they're identical atoms. Made identical, all in this wave function, they're identical. You got 10 to the 26 identical ones of them, you will not get the same energy. 36% of the time, you will get the energy of the second state. 64% of the time, you get the energy of the third state. How often will you get the energy of the first state? Never. How much will you get the energy of the fourth state? Never. Those two probabilities add to 1. This wave function has no first, it has no fourth, it has no fifth, it has no sixth. This thing is called entangled. It's in both states at the same time. In fact, quantum, if you take the Copenhagen interpretation, has no meaning to say what is its energy till you measure it. The very act of measuring creates the energy, if you will. And the uncertainty principle is because you can't know which place it will go, because it could go to either one. All you can say is that you could say, well, 36% times 64, I could find the average. Let's see, 0.36 times E2 plus 0.64 times E3 is the average energy. That's what classical physics will give me. So if I know these energy levels, I can tell you what the average value would be, but I'll never measure that. I'll only measure E2 and E3. And I will not be able to tell you which of those two I'll make on any measurement. I can measure an uncertainty. As we did statistics, we're supposed to be able to calculate an uncertainty now. And that's what the Heisenberg uncertainty is talking about. So that statistics was put in there for a reason. It wasn't unimportant. It was what we were going to deal with the rest of the semester. What's different is calculating probabilities, how we calculate it, not how we do the calculations of average and uncertainty. So if you didn't master that, you need to go back and make sure you do. Copenhagen interpretation is weird. You look at something and you change reality. That seems strange. You don't like that? A lot of people don't like that. I don't like that. But it works. Like, you like that. You got your hand up.
So what does it mean to, what criteria does something have to meet to be an observer to change a reality?
Any measurement. Anything that can make a measurement. Anything that can get information from the system. Tell you something else that's weird. You measure it. Measure an atom. And you find you get E2. If you were to make a bunch more measurements after that, you'll get E2 every time. 100% of the time. Nope. Which means that the act of measurement changes the state. We say it collapses it. It takes this vector out like here, and after we measure it, it folds it down to the state we measure, and now it's over here. And so it's got a new wave function. 100% second state. And it will stay there unless you measure something else whose axes are rotated with respect to this. Something that has an uncertainty principle connected to it. if you measure like position, and you measure and you get, hey, you're in the 2 meter position. You measure again 2 meters, measure again 2 meters, measure again 2 meters, 2 meters, 2 meters, 2 meters, never changes. Then you measure momentum, and you get whatever, 5 EV per C. And then you go back and measure position, you get 3 meters. When you measure momentum, it collapses the wave function into momentum states. And the momentum states are sums of the position states. So you move the axis, you move that vector off the axis now. And you changed its position by attempting to get information that you could not know. There is a limited amount of information that you can know at one time. If you attempt to ask for too much, you gain information of one type, you lose information of another. It's basically what the uncertainty principle said. Yeah?
We're going to do a lab of this nature.
Are we going to do what?
Like a lab that would...
Oh, yeah, right. No. No, there's no lab that I know of to do that other than getting a laser with a host of atoms. It's called graduate school. And you put a few, $1 million in and you go and do that. I'm sorry. I could make you roll dice or some bizarre thing. I probably could build something like that, but nothing really exciting like that. And we're not going to do a lot of those calculations about interpretation because we're going to leave that for your quantum person to spend lots of hours assigning lots of math. So I know you're going to enjoy that.
Okay.
That's what Dr. Quantum was talking about. When the observer looked and attempted to get information from the thing, he collapsed the wave function. That's what he meant by this. So a true system can always be written as the sum of the eigenstates. So what we solve for is the eigenstates, the unit vectors. Because if we know the unit vectors, anything else can be written as sums of them. So our problems in the class are to find the energy states, even though it may not be in the second state. It could be 22% in the second state, 31% in the third state, 15% of the fourth state, and so forth. It's in all states at the same time. That may be the real problem in the physical world. We just are going to worry about the individual states, not how to mix them as an electrical engineer. We'll leave that for the solid state classes and things like that. We're just going to get the states. And then we're going to move on, okay? So read that section about it. By the way, the most famous problem of collapsing a wave function is this problem. And I've given you some references. You have a box. And in the box you have a cat. See the big money I make in drawing. Good thing is, you do not have to be a great artist. I paint pretty good, but I don't draw as well.
He looks like Jade.
And that's my gun. I'm not going to use an AK-45 or something. I'm just going to use a regular gun. If this detector gets a particle that hits it, it fires a bullet and blows the head of this cat off. And over here is an atom, a nuclei, that's radioactive. But I won't know exactly when it decays because it decays quantum mechanically, so it has a probability. So I could write this as decay, don't decay. And at any instant, there's a vector out here, and it's got a certain probability that it's, when you square that length, it's decayed. And when you square this length, you find the probability it's not decayed. And that vector is moving around in space as a function of time. So it's tracing out some curve. Maybe like that. Now instead of saying decay and not decay, if it's decayed, it shoots. So the cat's dead. Dead cat. If it didn't decay, it's live cat. So to properly represent this, the cat must be simultaneously alive and dead. Now you do not know which, because you're not looked at the cat. And if you look at the cat, you make a measurement. So if you open the lid and look inside, the act of looking causes this arrow to either drop down on this axis and it becomes a dead cat, or it drops onto this axis and becomes a live cat with some probability. So the act of you looking at the box is what kills the cat. This is known as Schrodinger's cat. Now, this seems to be really bizarre because how the hell is cats live and dead and so forth? There was a thought experiment between Bohr and Einstein on this called the aspect experiment. It was eventually done off of it. And when it was done, Bohr was right, cats are live dead, and Einstein was wrong. Because that's what the data shows. Now they did it with atoms, not live dead cats, but the bottom line is it's the same thing. So it took about 40 years to ever get around, 50 years, before they could get the technology to do this very complicated experiment. But Einstein was wrong, Bohr was right. So the cat is a live dead. Now if you don't like live dead cats, I have a way around the live dead cats. In one universe, the cat is alive. And these probabilities are not probabilities of live dead cats, but they're different numbers of universes. And so if I have an infinite simultaneous number of universes with an infinite number of me talking and an infinite number of you listening, and then some you're listening and some you're not, of course I'm always in the wrong universe, we have actually just classical ones, but what measurement does is change the universe you're in. This is kind of one of this thing of the Planet of the Apes tried to use in one of the original books. So that's the many worlds interpretation point of view. What I know is this probability gives the right results, and classical physics gives completely wrong results. Yeah.
So you're saying in a parallel universe, Jaden can have a girlfriend and Philip can't?
That would be true. But those are low probabilities. The more probabilistic one is neither of those two can find a girl to get within 25 yards of. I should find a lot of blind girls.
I have a question though.
I saw a lot of drunk girls.
I saw on the news like a couple days ago that they claim that they think they can peek inside the box without pulling
Well,
it
the
in.
argument there is that in theory, if the uncertainty principle has more than one dimension, you might be able to squeeze uncertainty in one dimension while keeping it in the other. So for instance, in momentum and position, it's actually the product of delta px times delta y, delta pz times delta z, and so forth. So you can make something totally uncertain in the x, but well known in z. If all the information you're interested in is in z, and you don't care about x and y because it doesn't contain anything realistic, in theory you can put an infinite number, for instance, of information in a telecommunication packet. And Bell Labs has been trying to do that. I am not sure exactly what's going on with the whole argument on the photons, but the people that I know at A&M and elsewhere don't seem to have a problem with this interpretation still. That interpretation to the public isn't quite right. I will claim that I suggested you talk to Dr. Scully if you want to. The expert on quantum packets of light photon.
What does this do from the vantage point of the cat? What does the cat see in this box?
Cat doesn't see anything. Cat is the regular cat
It's just-
who experiences life. So this brings up the question of why don't you see? And of course, maybe it's because you're in different universes, right? We are getting into spooky philosophy here, okay, and leaving what? I can tell you what's going to happen. The math in quantum mechanics predicts the right thing and enables you to build devices that you cannot build otherwise if you don't understand this. My drawing of pictures is an attempt by a slow-moving, big, ugly object to attempt to explain the microscopic world. Probably a bad thing. It's like a person who's been blind and never seen anything attempting to explain a cribbage game. All right? But they were born on Mars and had never even seen what a playing card is yet. All right? And you're attempting to explain it. So you know, how much could that be perverted? Wheeler, John Archibald Wheeler, one of the great people of the Copenhagen 2 interpretation, if you read Nick Herbert's and Search Schrodinger Cat, or not, Quantum Reality, says the following, that the reason you appear to be on is because God is looking at your soul at this instant, thereby causing a collapsing of the wave function, thereby creating your reality. Hope he doesn't quit looking. Poof, you're gone. All right, so at that point, I think we can just leave and decide to move on to calculating the correct probability of mathematically forgetting the electron in the box or so. Certainly macroscopically we don't see this, but even if we did, the probabilities would be so small, just like angular momentum, it wouldn't be observable. But I know that you can't have an alpha decay, and you can't have an ammonia atom, and you can't have a transistor, and a nuclear bomb doesn't exist if you don't believe in this stuff. And I think Hiroshima was kind of the definitive test of that old stuff. And I would say the transistor, or Kilby, was pretty much, otherwise, why did you guys buy all these electronic devices that don't work? Because none of them can work according to classical physics. You can't have an iPhone. It's not possible, right? And to be honest with you, you can't have a calculator. No computer works. So I'm kind of convinced that this stuff kind of works. All right? I don't have any vacuum tube-based computers anymore in my house. All right? So it works. The interpretation, well, it obeys probability. You can't be a regular cat. That much is true. There's no doubt about that. People have attempted to find ways to put hidden variables. That is, you didn't measure something you should have. And if you knew that, it wouldn't have been so confusing. If it is, they go faster than the speed of light, and they don't obey a regular classical physics. And when you can actually move one point in space, you alter other points in space, thereby changing reality. So if a person is born in Denton, it actually could change what happens in France. That's what would have to be allowed in classical physics to get these sort of things. Well, that doesn't make me any happier. Okay, because I believe in causality, and I believe in localization, and I believe in all the regular stuff about physics. So we'll live with what we got. Cool stuff. But ain't going to be a lot of questions on that. It's going to be, can you calculate, be my particle, my box. Okay? This isn't philosophy 101 or theology, or can you give me the chief of the religion or something. Okay, one notice, can you calculate me that doggone electron in the box? The next thing he does, like I said, is he lowers the well. Now, the energy is going to be less than the well, otherwise the particle's free. By the way, there are those type of problems too, but I'm not going to deal with them because they're not in your book. I'll leave that for the quantum teacher. If you solve this, it's the same type of problem. You've got a region 1 where the potential is constant, a region 2 where the potential is constant, and a region 3. What's different now is, because that's not infinity, the wave function doesn't have to go to 0 anymore. And so I go through and I work that, but without working it, let's just take the difference, for instance, in the first state. In the ground state, before, we had this. This was the n equal 1 infinite well. Okay. Now, the middle looks the same as the problem before. So the middle should still look the same kind of when we solve the differential equation. But there is some probability now that it can be over in this well, since that well's not infinitely high. So it doesn't go to 0, it goes to something like that. And then it kind of exponentially decays. So there is some area here that the electron can exist outside the box. Now that seems kind of wrong, because how the hell does the electron get over there? Well, it turns out what the electron can do, if you want to think about it, is it can borrow energy. It can violate conservation of energy. As long as it borrows the energy for such a short time, it's within the uncertainty principle. Because you're only able to look within a certain amount of time. And conservation of energy is something that's been measured, and if it's measurable, it means that it took longer than the uncertainty principle to do it. So you've got a delta E delta T. Something like that. So if you borrow a little bit of energy, you only need a few dollars. Yeah, the bank's not too bad about it, so they don't really care too much to check on you, so they'll let you borrow for quite a long time. But if you decide to borrow $3 trillion from the bank gets really worried about this. They're going to be on your case quickly. Well, you wanted to borrow an infinite amount of energy before. You could borrow that for exactly 0 seconds. So you had no probability to get over here. So as you lower the well, the probability of getting into the well's walls goes up. Now, it's not going to matter. You're going to have to come back into the well and give it up. Unless, of course, we were to do something like this, which we will in a little bit, and bring this back down. And now you could borrow energy and get to the other side and then give it back. And then be a real particle again. And that's called tunneling. So you tunnel to a small thing called the base of a transistor, and you get over into the collector and continue on your way. And that's how you manage to increase the current. So if you change the width of that thing exponentially, you change the probability of the current. If you do that with a small control signal, that's how you build an amplifier in electrical engineering. So you expect the functions to look very, very similar. Same number of humps, same number of things, except they'll have these tails. Now, I went through, so get to have fun, to go through, to solve for all the coefficients, to eventually solve for one of the energy values. So I'll help you. The coefficients are nice, simple-looking things. And when you get done, you get to solve this equation right here. To find the eta, to find the energy levels of the allowed states. I say that looks a little harder than n squared times hc squared divided by 8 E naught L squared. That is the actual solution problem. Now, if you try to do that by hand, this is when computer tools are around, not for being stupid, but when you get to that. So I put in some values. What n is I said, look, I know the energy has to be less than U naught, so let it be some fraction of U naught. Plug that into my thing that I've solved for the equation, which is not so nice and simple, and I get this equation. I said, man, I don't know what the hell to do with the left-hand side. Maybe Dr. McCoy does. The right-hand side is -1. That I can handle. So what I'll do is I'll graph this on Excel and see everywhere it crosses the -1. So if I made the well